In the universe, certain objects hold particular interest for astronomers. These are binary stars. Their sheer number is astounding. It is believed that a significant portion of stars in the cosmos are part of systems comprising at least two celestial bodies. They help researchers unravel the universe's mysteries, determine its expansion rate, and measure distances to distant galaxies. Furthermore, they play a key role in a new field of physics, the study of gravitational waves. We often discuss the eventful life and eventual fate of our Sun, but the most dramatic processes likely occur during the evolution of multiple star systems. Stars in these systems can orbit at considerable distances from each other, or they can be in close proximity, sometimes even merging into a single entity. Over billions of years, these stars orbit together, significantly influencing one another, sometimes slowing down the aging process of a neighboring star, and at other times, accelerating it. Given the incredible diversity of multiple star systems in the universe, and the many different scenarios for their evolution, it is impossible to cover this topic in a single episode, even if it were 40 minutes long. Therefore, their story will be presented in at least 2 parts within this video series on stellar evolution. No one is surprised by the fact that the distances between stars are so vast they are difficult to comprehend. Even the distance of a few light-years to the nearest stars is astronomical compared to their sizes. How, then, were astronomers able to discover and study stellar systems and understand that they consist not of one star but of several, when they are hundreds or even thousands of light-years away from us? Are modern telescopes truly capable of resolving 2 stars at such incredible distances? Or is their duplicity perhaps determined by indirect indicators? The answer to this question is much more complex than it seems, so let's first understand what binary and multiple stars are. It probably won't surprise anyone to hear that a binary star is a system consisting of 2 stars. However, there's an important clarification. We are talking about gravitationally bound stars orbiting in closed paths around a common center of mass, which scientists call the barycenter. Among these 2 stars, one is designated as the primary and the other as the secondary, often called the companion star or satellite. This distinction is based on brightness or mass, depending on the specific scientific study. A similar definition applies to multiple systems, which include 3 to 10 stars. All of them must stably orbit around a common center of mass. When designating individual stars, a Latin letter is added to their name in descending order of mass. For example, the triple system Alpha Centauri consists of the primary star Alpha Centauri A, and the companion stars Alpha Centauri B and Alpha Centauri C. The latter is more famously known as Proxima Centauri. In addition to physically binary stars, which are genuinely binary, there are also optically binary stars, which are not. They may appear as a pair but are actually at different distances from the observer and are simply projected onto the celestial sphere in the same direction, having no physical connection between them. Conversely, not all truly binary systems can have their duplicity determined. Firstly, in binary systems with very large separations between components and orbital periods spanning thousands of years, it is not always possible to establish that the stars are indeed orbiting a common center of mass. Secondly, in systems where the luminosity of one star is thousands or tens of thousands of times greater than the other, the companion star can be detected almost exclusively if the system is eclipsing. Using other methods is extremely difficult. Thirdly, due to the immense distances to stars, we may simply not be able to see both components of the system separately. The first person to suggest that some optical pairs must be physically connected was the English clergyman John Michell in 1767. He statistically proved that the number of optical pairs observed by astronomers even then was too large to attribute to mere chance. Michell concluded that stars must gravitationally interact with each other and form systems consisting of more than one star. Later, his hypothesis was confirmed by both direct observations and numerous indirect pieces of evidence. Binary stars indeed exist. Surprisingly, most stars in the universe are found in systems containing 2 or more components, while single stars, like our Sun, are rarer. To understand the reasons behind this phenomenon, it is worth recalling how stars form. Currently, scientists have 2 main theories for the formation of binary stars, each describing several scenarios for astronomical events. The simplest seems to be the formation of a binary system from two single stars that accidentally combine into a system as they pass each other. They attract each other and form a system, meaning gravitational capture occurs. Although this hypothesis was popular for some time, it was later rejected by scientists as the primary mechanism. While such binary system formation is indeed possible, theoretical calculations show that this scenario is very unlikely. This unlikelihood is explained by a combination of two factors. Firstly, the two stars must pass close enough to each other for the gravitational influence to be sufficient. This distance is hundreds of times smaller than the average distance between stars, which already makes the phenomenon statistically improbable. Secondly, for the stars to enter a stable orbit, their angular momentum, which depends on their speed relative to each other, must be within a certain range. If the speed is too high, mutual attraction won't be able to compensate, and the stars will just fly past each other, which is often what happens. If the speed is too low, both stars will simply collide before entering a stable orbit. Currently, the prevailing scientific view is that the vast majority of binary and multiple star systems are born as such. Earlier, the existence of molecular clouds was mentioned, where hundreds of regions of higher density form. During their evolution, these regions gradually merge, forming larger structures that later become stars and planets. Due to the significant distances between them, reaching several light years, not all large concentrations of matter manage to merge into a single entity during formation. Consequently, the most likely scenario for the appearance of a multiple system, or even a small star cluster, is direct formation from a molecular cloud. Some star clusters eventually disperse, giving rise to single, binary, and multiple stars. Such a chaotic and unstable nature is typical for these systems. However, under certain initial conditions, a star cluster can maintain its integrity for hundreds of millions of years. A prime example is the Pleiades cluster, which contains over 1,000 stars aged between 75 and 150 million years. Despite ongoing discussions about the exact percentages of stars of different multiplicities, it is well established that most stars, at least within the Milky Way, are part of binary systems. Modern research indicates that binary stars account for an average of 60 to 70% in our galaxy. Single stars make up only 20 to 25% of the total number of celestial bodies. Triple systems constitute about 10%, and systems of 4 stars are less than 1%. There are systems consisting of 8 and even 9 stars, but currently, only 2 such systems are known, Gamma Cassiopeiae and QZ Carinae, discovered relatively recently. To understand the functioning and evolution of binary and multiple star systems, which is one of the most fascinating areas of astrophysics, it is necessary to grasp the peculiarities of stellar motion in various systems. Given the complexity of multiple systems, it is advisable to begin with a detailed study of stellar motion in binary systems. Stars in such systems move in elongated orbits around an imaginary point called the center of mass. Each star traces an ellipse with this point at its focus. The center of mass, or barycenter, is located closer to the more massive star. In detached systems, where the distances between stars are many times greater than their sizes, the eccentricity of the orbits can take various values, up to close to unity. In semi-detached and contact systems, where the semi-major axis of the orbit is comparable to the sizes of the stars, the orbits become more circular, and their eccentricity does not exceed a few hundredths. Such stars are often tidally locked, always presenting the same side to each other. Among the parameters of binary stars used by scientists, the most important are the mass ratio and the ratio of the orbit radius to the sizes of the stars. The mass ratio is the ratio of the mass of the less massive star to the mass of the more massive one. This parameter is important because it can be directly measured from spectroscopic observations, particularly from the radial velocity curve. Moreover, it is the mass ratio, not individual masses, that is used in most formulas for calculating system parameters. The mass ratio has limitations. The maximum value is 1, for identical stars, and the minimum is determined by the fact that the smallest stars must have a mass of at least 8% of the Sun's mass. One of the smallest observed mass ratios is in the GSC 0180402226 system, which is approximately 0.043, 1 to 23. This system consists of a dwarf with 7% of the Sun's mass, and a star that is more than 1.5 times as massive as the Sun. The ratio of sizes to the average distance between the stars is a more complex parameter because stars in a system often have different masses and sizes and can be at different stages of evolution. For example, one of the stars might be a red giant. To understand the further evolution of binary systems, astronomers use a parameter called the degree of Roche lobe filling, which plays a key role in the processes occurring in binary systems. The Roche lobe, a concept born in the minds of scientists, is a cornerstone in understanding the metamorphoses that occur in binary star systems. Named after the French astronomer Edouard Roche, it represents a boundary, a limit to a star's domain, in a close binary system. In other words, it is an imaginary region around a star that defines its maximum size. If a star swells so much that it extends beyond this boundary, its outer layers will begin to flow onto the neighboring star, like a river overflowing its banks. In a binary star system, stars are affected not by two, but by three forces: the gravitational attraction of each star and the centrifugal force arising from the system's rotation. It's important to note that we are considering a reference frame in which both stars are the main actors. As a result of the complex interaction of these forces, the imaginary Roche lobe is formed, resembling two teardrops connected at their tails at a common point. It should be emphasized that this connection point is not the system's center of mass, as it might seem at first glance. These are two different points that coincide only in one unique case, when the masses of both stars are absolutely identical. In the general case, the center of mass is located closer to the more massive star, while the connection point of the Roche lobes is shifted towards the less massive star. So what exactly is this connection point between the two Roche lobes? It is none other than the Lagrangian point L1. For those familiar with celestial mechanics, this concept is not new. For others, let's explain. Every two-body system, be it binary stars, the Earth-Moon system, or even the Earth-Sun, has 5 special points called Lagrangian points. At these points, the gravitational forces of both bodies and the centrifugal force reach equilibrium. Although there are 5 Lagrangian points, in the context of binary star systems, L1, also known as the inner Lagrangian point, is of greatest interest. It connects the two Roche lobes, and it is where the gravitational forces of the two stars and the centrifugal force balance each other. And, as you might have guessed, it is L1 that plays a key role in the process of mass transfer between stars. However, the equilibrium of forces at the Lagrangian points is a rather conditional concept, as it is unstable. The slightest deviation from point L1 causes the resultant force to begin pulling the object towards one of the stars, and the greater the deviation, the stronger this force. For similar reasons, points L2 and L3 are unstable, while points L4 and L5, also called triangular points, become stable only with a sufficiently large mass ratio, as, for example, in the Sun-Jupiter system. Within each of the teardrop-shaped halves of the Roche lobe, the gravity of one of the stars dominates, or more precisely, a combination of gravity and centrifugal force. The size of these halves depends on the mass of both components of the system and the distance between them. Hereafter, when referring to the Roche lobe, we will mean half of this cavity, corresponding to a particular star. Thus, in a binary system, a star can be in one of 3 states relative to its Roche lobe. It can be located deep inside it, it can fill its Roche lobe, or it can even overfill it, extending beyond its boundaries. It is these states of Roche lobe filling for the two stars that largely determine their subsequent evolution, sometimes even more so than the initial mass of each star. It is worth noting that in many cases, the size of the Roche lobe also limits the size of the star itself, because if it expands beyond the lobe, its atmosphere will begin to be stripped away by the companion's gravitational pull. This material, like previous ones, is the result of meticulous collection and analysis of information from dozens of scientific and popular science articles, carried out by a team of enthusiasts passionate about popularizing astronomy and scientific research. Now that we have covered the formation of multiple systems, the Roche lobe, and Lagrangian points, we can move on to the most exciting part of our discussion, the evolution of binary systems. It is incredibly diverse, and even a multi-hour video would not be enough to describe all possible scenarios. Therefore, we will focus on the key types of binary stars. Since there are 2 stars in the system, various combinations of Roche lobe filling are possible, which astronomers group into 4 main types: detached systems, where both stars are deep inside their Roche lobes; semi-detached systems, where one star fills or almost fills its lobe; contact systems, where both stars fill their Roche lobes; and over-contact systems, where both stars overfill their Roche lobes. Moreover, throughout their evolution, each star in the system will change its size and, consequently, its category. Let's imagine a system where 2 stars are on the main sequence and have a long orbital period. In this case, the distance between them is large and significantly exceeds the sizes of the stars themselves. An excellent example of such a system is the binary star Eta Cassiopeiae, discovered by William Herschel way back in 1779. Due to its 480-year orbital period, it has completed less than half an orbit since then. The distance between the 2 stars reaches about 70 astronomical units, which is almost double the semi-major axis of Pluto's orbit. The stars are so far apart that they can even be seen as 2 separate objects. In such a case, either star fills its Roche lobe, and they evolved independently for a long time, with virtually no interaction. Furthermore, stars don't necessarily need periods of hundreds of years to be considered detached. A significant portion of all binary stars with periods ranging from a few tens of days to tens of years are detached. Semi-detached stars represent a fascinating link between contact and detached systems, where exciting cosmic processes unfold. In these systems, the stars are located at a relatively small distance from each other, which immediately affects their rotation. Their orbits become almost perfectly circular, and both celestial bodies often become tidally locked, as if dancing in a gravitational waltz. Particular interest arises when 2 stars show a significant difference in surface temperature, reaching several thousand degrees. In this case, the hotter star begins to noticeably heat its cold neighbor. On the surface of the latter, in the region closest to the scorching companion, a large hot spot forms. The temperature of this spot can exceed the temperature of the rest of the star's surface by thousands of degrees, and its area can range from 10 to 15% of the total surface. This phenomenon is called the reflection effect, although the English term does not perfectly capture its essence. The star's surface is not a mirror reflecting light. Rather, this process resembles what happens inside stars, where photons are absorbed and almost instantaneously re-emitted. The only difference is that in this case, the additional energy flux comes not from the star's core but from its hot neighbor. Astronomers easily detect this effect, especially if the binary star is eclipsing, meaning the stars alternately pass in front of the observer. Eclipsing binary stars are characterized by 2 distinct minima in brightness, corresponding to the eclipses of each star. However, when one star heats the other, the depth of the eclipse becomes shallower due to the significant brightness of the hot spot. In extreme cases, the effect from the spot can be so strong that the system's total brightness during an eclipse even increases relative to the out-of-eclipse phase. But the most exciting phenomenon occurring in semi-detached systems is the transfer of matter through the first Lagrangian point. When one star almost fills its Roche lobe, it loses its spherical shape and deforms under the influence of the companion star's gravity, as if stretching in its direction. At a certain point, the nose of the star stretches so much that it critically approaches the first Lagrangian point, and the gravity of the second star begins to pull gas towards itself. This process of mass transfer is called conservative or pseudo-conservative because the total mass of the system remains practically unchanged, but there is a redistribution of mass between the stars. According to the laws of orbital mechanics, if mass flows from a more massive star to a less massive one, the distance between them decreases, and vice versa. These changes in distance, even with constant mass, directly affect the system's orbital period. One of the most interesting examples of a semi-detached system is Beta Persei, also known as Algol. This system, as discovered in 2009, is a triple system. However, the two main stars form precisely a semi-detached system in which mass transfer occurs. Here arises the Algol paradox. The less massive star of the system has already evolved into a subgiant, while the more massive star is at an earlier stage of evolution. According to modern understanding of stellar evolution, massive stars age and die faster. The solution to this paradox lies in mass transfer. The rate of transfer is low, about 1/billionth of a solar mass per year, which is typical for such systems. However, over billions of years of the system's existence, the initially more massive star evolved, expanded, and transferred most of its mass to its neighbor, which was initially less massive. As a result, the mass distribution in the system changed, and the star that was previously less massive became more massive, but it is still on the main sequence. Thus, even in systems that are not in contact, the presence of a second star has a huge impact on the evolution of each celestial body. In contact systems, mass transfer also occurs, but significantly more intensely than in semi-detached systems. The transfer rate can reach several millionths of a solar mass per year, which is 3 orders of magnitude greater than in the previous case. In some types of binary systems, the rate of mass transfer can even reach several thousandths of a solar mass per year. Due to such intense transfer, stars change their masses more quickly. This means that when one of them evolutionarily increases in size, it almost instantaneously sheds excess mass to the other. As a result, the evolution of one of the stars in the system slows down, while the others accelerates. Unlike detached and most semi-detached stellar systems, contact and overcontact stars are characterized by a gradual reduction in their orbital radii. In isolated systems, the loss of total angular momentum occurs extremely slowly, primarily due to viscous friction with the interstellar gas that stars themselves expel as stellar wind. However, there are other slowing mechanisms. For example, general relativity predicts that gravitational waves carry not only energy but also angular momentum, leading to the breaking of stars and their closer approach. Nevertheless, for ordinary stars, this effect is insignificant compared to other factors. Gravitational waves significantly influence the reduction of orbital radius only in systems consisting of two compact objects. Another way a binary star loses angular momentum is related to magnetic braking. Any star with a convective envelope, similar to our Sun, slows its rotation due to the interaction of stellar wind with its magnetic field. This explains the relatively slow rotation of the Sun around its axis. A similar process occurs in binary systems where stars interact not only gravitationally but also through the electromagnetic field. However, all these braking mechanisms act extremely slowly, and the changes they cause often remain imperceptible even over the lifetime of the stars. In contact systems, the situation changes drastically. Here, there is a flow of matter significantly denser than the interstellar medium, leading to viscous friction between it and the second star. In such conditions, the change in orbital radius can range from a few percent to a significant reduction, even leading to the merger of the two stars into one. A striking example of such a system is Beta Lyrae, the prototype of the eponymous type of eclipsing binary stars. In this and similar systems, both stars are noticeably elongated towards each other due to mass transfer. The period of this star has already undergone significant changes. In 37 years, the orbital period increased by almost 50 minutes, and over more than 230 years of observations, the change was more than 1%, a significant amount by stellar standards. There are also binary systems that may seem strange and even fantastical. These are systems in which both stars exceed their Roche lobes, and their photospheres, meaning the lower layers of their stellar atmospheres, envelop both stars. In such systems, the temperatures, sizes, and masses of the stars are usually similar, and the system's shape resembles a dumbbell. Such binary stars are called overcontact binaries or common envelope stars. An example of such objects among variable stars is W Ursae Majoris. Interestingly, mass transfer in such systems is not always observed, although it would seem that due to the star's proximity and the extensive contact zone, it should be intense. In reality, transfer rates are indeed very high, reaching 1/10,000th of a solar mass per year for massive overcontact stars. However, this process is so short-lived that it is difficult to detect. The astonishing features of overcontact systems are not limited to their appearance. At the end of their evolution, they undergo equally impressive transformations. If stellar matter reaches Lagrangian points L2 or L3, it can begin to flow off the star's surface, forming a gaseous disk that envelopes both stars, creating a common envelope. Common envelope stars experience an extremely unusual stage of evolution. As they orbit each other, the stars interact with the common envelope, leading to friction. This causes a loss of angular momentum, and the stars spiral inward. Additionally, viscous friction heats the envelope, which sometimes leads to its ejection. In such systems, the stars are situated extremely close to each other. The distance between them can be less than the sum of their diameters. Friction intensifies further, rapidly slowing the star's rotation. This causes their orbital radii to decrease, eventually leading to the common envelope, along with the star's outer layers, being expelled into space. Ultimately, only the core and its innermost layers remain of the star from which the mass transfer began. However, there's another, more dramatic outcome for stars in a common envelope. If the energy released during their close approach is insufficient to eject the envelope, both stars merge into a single, more massive star. This phenomenon is known as a common envelope event. During such a merger, the star's outer layers are ejected into the surrounding space, exposing the hotter interior layers of the newly formed star, leading to a hundreds-fold increase in total brightness. Interestingly, after a merger, the cores of both stars can remain distinct within the unified atmosphere, forming a unique cosmic egg with two yolks. This phenomenon is not as rare as one might think. Astronomers estimate that 5 to 10% of all stars conclude their evolution in such a merger. This is attributed to stars changing the degree to which they fill their Roche lobe during their evolution. Sometimes, a binary star system progresses through all stages, from detached to semi-detached to contact, then supercontact, and finally experiences a merger. Undeniably, binary stars are among the most captivating phenomena found in the vast expanse of the universe. The meticulous study of these systems is crucial for a deeper understanding of key stages in stellar evolution, the complex interactions between stars, and the physical conditions prevalent